Good morning all. Last day we have the definition of cosets and 2-3 examples of cosets. Today also we are continuing the examples of cosets. We have a group G and let H be a subgroup of group G. Then the left coset is a capital H which is equal to set AH, a small h where H element of capital H, which is the left coset of capital H containing A. Similarly, we can define the right coset of H containing A, HA, which is equal to HA such that small h element of capital H. Upper left coset angle we have AH and right coset is HA. And we did 2-3 examples. Given S3 equal to rho 0, rho 1, rho 2, mu1, mu2, mu3. The symmetric group of 3 letters and a subset H is equal to rho 0 mu1. Then we have to find the right and left cosets of H, and we have to show that it partitions the S3. So first we have to write the elements of S3. First 3 rotations 1 2 3 1 2 3 1 2 3 rotating 2 3 1 and again rotating 3 1 2 1 2 3 3 1 2. Next we have reflections. We keep one fixed and reflection of 3 and 2 1 2 3 1 3 2. Here 1 2 3 3 2 1. We keep 2 here and reflection of 3 1. Mu 3 we will keep 3 here and reflection 1 2 and 2 1. 1 2 3 2 1 3. So we wrote the multiplication table of S3. We know that rho 0, rho 1, rho 2, mu1, mu2, mu3 are the elements, and the multiplication table is in the first row rho 0, rho 1, rho 2, mu1, mu2, mu3. In the second row with operation with rho 1. So rho 1, rho 2, rho 0, mu3, mu1, mu2, rho 2, rho 0, rho 1, mu2, mu3, mu1, mu1, mu2, mu3, rho 0, rho 1, rho 2, mu2, mu3, mu1, rho 2, rho 0, rho 1, mu3, mu1, mu2, rho 1, rho 2, rho 0. So given we have given H equal to rho 0 mu1. Here our composition is permutation multiplication. And the left cosets are left coset containing H is MH where H element of capital H. So here we can take the rho 0 itself. Let rho 0 element of H. So consider rho 0 H, which is equal to rho 0 into H element of rho 0, rho 0 into H, the other element is mu1, which is equal to rho 0 is equal to rho 0, and the other one is mu1. Now rho 1 not an element of which is same as H. Now rho 1 is not an element of H, and consider rho 1 H, which is equal to rho 1 rho 0 rho 1 mu1. Rho 1 rho 0 is rho 1, and rho 1 mu1 is, we can take this multiplication table. So rho 1 mu1 is mu3. Now row 2 not an element of H union row 1 H, the two left cosets. So we can consider row 2H, which is equal to row 2 row naught, row 2 mu 1, which is equal to row 2 row naught is equal to row 2 and row 2 mu 1 is equal to mu 2. So we got row 2H and H union row 1H union row 2H is equal to, we have row naught, row 1, row 2 and mu 1, mu 2, mu 3, which is equal to S3. That is H row 1H and row 2H are disjoint sets, that partitions S3. And H row 1H and row 2H are left cosets of H Good morning all. Last day we have the definition of cosets and 2-3 examples of cosets. Today also we are continuing the examples of cosets. A coset is, we have a group G and let H be a subgroup of group G. Then the left coset is set AH, a capital H, which is equal to set AH, a small h, where H element of capital H. അതായത് A എന്ന് പറയുന്ന which is the left coset of capital H containing A. Similarly, we can define the right coset of H containing A, so HA, which is equal to HA such that small h element of capital H. അപ്പോൾ left coset ആണെങ്കിൽ we have AH and right coset is HA. And we did 2-3 examples. Today we have Now the right cosets of H are HM, which is equal to H small m, where H element of capital H. So consider first row naught element of H. So consider H row naught, which is equal to row naught mu 1 row naught, which is equal to row naught and mu 1, which is same as H. Now since row 1 not an element of H, consider H row 1, which is equal to row naught row 1, row naught mu 1 row 1, which is equal to row naught row 1 is same as row 1 and mu 1 row 1 is, we have the table here, mu 1 row 1 is equal to mu 2. Now row 2 not an element of H union H row 1. So consider H row 2, which is equal to rho naught row 2 mu 1 row 2, which is equal to rho naught row 2 is same as row 2, mu 1 row 2 is mu 3. Therefore, H row 1 and H row 2 are the right cosets of H, and they are disjoint. And H union H row 1 union H row 2 is equal to S3, that is right cosets of H partitions S3. Now fifth problem is for a subgroup H of G and for a element of G, prove the following. First one, HE equal to H. Second one, a element of HA. അത് രണ്ടുമാണ് ഈ പേജിൽ പ്രൂവ് ചെയ്തിരിക്കുന്നത്. For the first one, we have to show that given that H is subgroup of G and a element of G, and we have to show that HE equal to H, where E is the identity element. We know that E is the identity element, so HE equal to H for all H element of H, the property of identity element. So the right coset HE is defined as small set of all HE such that H element of capital H. This HE equal to H, so H such that H element of capital H, which is capital H itself, the set H itself. So the A is put. Now next B is a element of HA. We have, since H is a subgroup of G and the identity element E of G is an element of H, so E is an element of H, which implies EA element of HA, which implies a element of HA since EA equal to A. Now see, we have to show that a element of H if and only if H equal to HA, given that H is subgroup of G and a element of G. We have here if and only if, we have to show that both sides. So for that, first assume that let a element of H, then choose any B element of HA, then B is equal to HA for some H element of H. Since H is subgroup of G, it is closed with respect to induced operation. So our two terms A and B, H element of H and A element of H implies HA equal to B element of H. So B element of HA implies B element of H. So HA is contained in B. Now choose H element of H and A element of H. So HA inverse element of H. So HA inverse into A, which is equal to H into A inverse A, which is equal to H element equal to H. A inverse A is identity, so only H will be there. So H element of HA. Thus H element of H implies H element of HA. So H is contained in HA. Here we have shown that HA is contained in H. Also H is contained in HA, which implies H equal to HA. Conversely, assume the next part, HA equal to H. Since H is a subgroup of G, the identity element is an element of H. So A equal to EA element of HA is equal to H. So we shown that A element of H. Now we have to show that HA equal to HB if and only if AB inverse element of H. So given H is a subgroup of G and A comma B element of G. First let assume that HA equal to HB. Since H is a subgroup, E element of H, and so A equal to EA element of HA equal to HB. Therefore HA equal to HB implies A element of HB implies A equal to HB for some H element of H, implies AB inverse equal to HB into B inverse, which is equal to H into B inverse, which is equal to H into B inverse, which is equal to H B inverse, which is equal to HE equal to H for some H element of H, implies AB inverse element of H. Conversely, AB inverse, assume that AB inverse element of H. Then X element of HA implies X equal to HA for some H element of H. So X equal to HA into E. X equal to HA ആണ് നമ്മൾ ഐഡന്റിറ്റി വെച്ച് മൾട്ടിപ്ലൈ ചെയ്തു. So E is equal to B inverse B. So HA into B inverse B, which is equal to, we can combine these three terms, HA B inverse B, which is element of HB. Since H element of H and AB inverse element of H implies HAB inverse element of H. So this term is element of HB. So now assume that X element of HB, which implies X equal to HB for some H element of H, implies X equal to HB into E, which is equal to നമ്മൾ നേരത്തെ ചെയ്തെടുത്ത same step, HB into A inverse A, which is equal to HB A inverse into A element of HA. Since H element of H, AB inverse element of H implies AB inverse H, which is HBA inverse element of H. Thus X element of HA implies X element of HB, which implies HA equal to HB. Now sixth problem, let G be a group and H be a subgroup. Prove that the number of left cosets of H in G is equal to the number of right cosets of H in G. അപ്പോൾ നമ്മളിവിടെ ചെയ്യാനായിട്ട് we will take the collection of all left cosets and right coset, and we are giving a function and show that function is 1 1 and 2. So first we take the collection of all left cosets of H in G as CL, and CR be the collection of all right cosets of H in G. Then CL is equal to AH, where A element of G, and CR is equal to HA, A element of G. Now define psi from CL to CR by psi of AH equal to HA inverse. അപ്പോൾ ലെഫ്റ്റ് കോസറ്റ് നിന്ന് റൈറ്റിലേക്കുള്ളത്. For any AH BH element of CL, psi of AH equal to psi of BH implies HA inverse equal to HB inverse, which implies A inverse equivalent are B inverse, which implies A inverse B inverse or inverse is equal to A inverse B element of H. So which implies A equivalent LB implies AH equal to BH. Hence psi is 1 1. Now choose any HA element of CR. Then A element of G, so A inverse element of G, also A inverse H element of CL, and psi of A inverse H is equal to HA inverse equal to H. Hence psi is on 2. Since psi from CL to CR is 1 1 and on 2, CL has the same number of elements as CR. Hence CL is the number of left cosets of H in G, which is equal to the number of right cosets of H in G.